Welcome everyone to Young Hydrologic Society's webinar on causal discovery tools and their application hydrometeorology. Let me start with a small description about the speaker. Mr. Tejasvi Chauhan is an MTech and PhD candidate at the Indian Institute of Technology, Bombay. He was a Prime Minister Research Fellow. His work focuses on causal discovery tools in hydrometeorological systems at varying spatio-temporal scales. He has recently submitted his PhD thesis at IIT Bombay, and currently he joined his postdoc at the Max Planck Institute for Biogeochemistry in Germany. And congrats for that. And stage is yours.
Thank you, Avinash. I'll share my screen. Is it visible?
Yeah, it is visible.
Yeah. Okay. Thanks for the introduction, Avinash. Hello, everyone. Welcome to this seminar on webinar on tools for causal discovery and their applications in hydrometeorology. This is a bit redundant since Avinash already introduced me, but here's a brief info about myself. I'm a civil engineer. I've done my bachelor's in civil engineering from National Institute of Technology, Hamirpur, Himachal Pradesh, India. And post that, I joined as a master's student at IIT Bombay, and thereby converting to MTech plus PhD dual degree. I've submitted my thesis at IIT Bombay, and currently I'm a postdoctoral fellow at Max Planck Institute of Biogeochemistry. So here is a brief outline of how this talk is going to be structured. First, I'll introduce what causal discovery is about. Why is it important? Next, one second. Yeah. Next, I'll introduce various tools that are available for causal discovery. Post that, I'll share two of my case studies that two of all my objectives from my PhD where we have applied these methods. And then we'll discuss some challenges that lie ahead in causal discovery techniques. So let's start with the introduction. So what is causal discovery all about? So the whole idea of causal inference lies in the paradigm of prediction. When you want to predict something using statistical models, of course, then you want to make sure that the variables that you are using are true predictors. So that's what causal discovery is all about. Are we using correct variables for predictions, or are we getting good predictions for due to wrong variables? So that's the whole idea. And then there are things like trying to find out what would happen if I change something, what would have happened if things had happened differently. These kinds of questions can also be answered using causal discovery. So in a sense, if you are using a machine learning algorithms with the advent of with growing technology, as we get more and more data-driven techniques are going to be more and more useful with time. But to ensure that we are using correct predictors, causal discovery can help. So causal discovery, with causal discovery, we can answer some deeper question about anything that you are trying to study. So here is a table which tries to tell different layers of causal hierarchy, different degrees of depth in which questions can be answered. This is from a book by Udia Pearl named The Book of Why. So the first is questions that only try to answer whether or not there is an association. So this hierarchy, it is the lowest form of depth of knowledge that you want to gain. What we want to target here is how would seeing a variable, seeing a value system X change my belief about Y? If I already know about X, how much do I already know about Y? Things like that. So our statistical weather forecasts, correlation-based methods, pattern recognition, or a simple medical science statement like aspirin is associated with reduced headaches lie in this hierarchy. It does not tell us about mechanistic pathways, but it tells us about statistical associations, that yes, these things are associated. A second depth of question that can be answered is regarding interventions. So here, what if statements come into the play? What if I do X? So what if we increase greenhouse gas emissions? How would the future look like? Now, this is way different than a plain association-based question. So this question has some degree of depth to it because an intervention is involved. So this is a second degree of question causal hierarchy that we can try to explore. Third is counterfactuals. Now, this layer of causal hierarchy has to do with something called imagination and retrospection. So let's say something has already happened. Past year, let's say droughts occurred, floods occurred. Now we want to either ask an imaginative question or a retrospective one. Retrospective in a sense that was it the El Nino or La Nina that caused our drought or floods, or it could be imaginative. Had the have if El Nino increases, what would given this has already happened, if this changes, if El Nino changes, how would these things change? So in this, if you ask questions in this sense, it becomes even more deeper in sense of knowledge and mechanisms, and these are called counterfactuals. So causal discovery based methods try to answer questions in these two paradigms. Now, why is all this important in earth science? It's because earth system is very complex with many internal feedbacks at varying time scales. So on a broader scale, what Earth is trying to do is it's trying to make some energy balance based on solar radiation that's received from the sun, and Earth emits it out. But internally, there are many processes that make it happen. While from the path when light is absorbed by the Earth and to the emission, a lot of stuff happens, which has multiple time scales. And a lot of these processes in our climate models are still not resolved. We parameterize a lot of things. So because of these complex internal feedbacks, a lot of stuff is not known till now. But if we are increasing our observations, if data availability is rising, observed data has a huge amount of knowledge to be found if we use appropriate methods. So causal discovery can be used in earth science in this sense that we can reveal relationships which were not known before, or use them to generate some statistical models, machine learning based models as data science advances, to use appropriate predictors. Now, in this paradigm of causal inference, there are two steps involved. Once we have decided that we are going to go ahead with causal inference, there are two steps that need to be done. One is called causal discovery, and the second step is called cause effect estimation. Now, let's say you have data available. So the causal discovery phase has to do with identifying the causal structure. What is linked to what? In a true sense, if we let go of correlation, if we ask process-based questions, which thing is linked to which variable is linked to which variable? What does the structure look like? So to answer this question, we perform something called causal discovery. And once the causal structure has been identified, the next step is to estimate the effects that are lying in the structure. So for example, each and every link has been, let's say you have identified that yes, in terms of yes, no questions, these links exist between these variables. And now then second step would be to identify how strong are they. So these are two in real life. This is what it would look like. Does El Nino cause a change in interannual variability of monsoon? Plain yes no question. It could be yes if these two had been nodes of El Nino and Indian monsoon. But next step would be to identify by how much. So you try to assign some strengths to these links. So this step is called cause effect estimation. These are two different things, and various methods are targeting two different things. There are methods developed for these two different things. Now, before we move further into tools that are available to do what I just explained to you, since this is all statistical based on data, there are some assumptions involved. So here are some important assumptions that I'm listing here. There are a lot more which vary based on your link type you want to study, based on data, based on the processes. It could be anything. But the major assumptions are, first one is called causal sufficiency. It assumes that there are no hidden common drivers. Now that's very important, because if there is a common driver, so this node, let's say it causes these two, then if it is absent in your data set, there is no way to find out that, no way to know that this link is actually not true. If A causes B and C, then B and C will automatically be shown as connected if you use some bivariate method. There will always be correlation between them, treatment and outcome. But if you don't know the confounder, this variable which causes both variables is called a confounder. If you don't know the confounder, if you don't have any information about it, you will obviously treat them as correlated, and it won't be a mechanistic explanation. So causal sufficiency assumes that your prior knowledge contains this information, that data already has all the necessary confounders. Then there's a Markov condition, which assumes that once you have identified the parents are called, which have direct links to our variable of concern. So let's say in this slide, the variables which are this node here has three parents, 1, 2, and 3. So the immediate links, when you have identified, everything else becomes irrelevant. That's what Markov conditions tells us. Once you have identified the parents, their past does not matter in prediction. The next is called faithfulness. Now, faithfulness assumption tells us that graph that we have generated of nodes and links contains all necessary conditional independence relations that make sure Markov conditions. So what this means is, I'm sorry. What this means is that if these links are present, they can be delineated by calculating conditional independence. So if a link is absent, given that Markovian chain is being followed, the conditional independence will ensure that that link is absent. So that's faithfulness. Together with Markov condition and faithfulness, if you perform a conditional independence test between any two time series and it comes out to be this, they are conditionally independent, then that you can assume that there is no link between them. And then there is an assumption about instantaneous effects. So it assumes that there are no instantaneous causal relationships. Most of the causal discovery algorithms are founded on this assumption that there is a precedent structure in the data set. So cause must precede the action. Next is stationarity. It is very conventional assumption. So stationarity means that the causal structure is invariant in time. And then there is type of dependency, whether or not are we assuming that things are all linear, or are we assuming non-linear, what kind of non-linearity, and so on. So now assume that you guys have an idea what causal discovery is all about. What are the important things? What's the concept? What are we going to do? So now we know that it's all about data sets. So observed data, we are trying to find out what are the best predictors. So now tools to do that. We'll jump to the tools that are available to do that. So the most conventional and most famous tool that is available, that is well known, is called Granger causality. It's named after the guy who proposed this. And what it does is it uses prediction to find out the causality. So if, let's say, we have a variable x, we have variables x, y, z, and w, and I test a linear regression where addition of y adds some significant predictive information to the system, to w, then I'll announce that y Granger causes w. That's all. So if any variable can add, if lagged variables can add significant predictive information to any variable, we announce them that yes, the Granger cause the variable of interest. It's as simple as that. Now, what are the caveats here? For to understand, since only linear regression will be used, the links that you find would be linear. So there could be a nonlinear system and you won't detect it at all. Now, confounders become a big problem here. Since you will stick to bivariate analysis, confounders will be a problem. If you go to multivariate analysis, then curse of dimensionality starts to pop up. Each and every variable at multiple lags become many, many dimensions. So so it becomes complex, and we lose statistical power. So we lose trust in our links as number of nodes increase. And then separability is one more thing that is problematic here. For a system in which two variables are, let's say that there had been an equation where w is multiplied with y, or where, for example, w depends on some not linear or a separable function of y, but inseparable function of y with x, y into x, or y sine x, or something like that, then Granger causality would fail. So separability is a necessary condition for if you want to perform Granger causality. Now, next theory that offers some tools to us is called information theory. So I'll briefly introduce what information theory is about. So let's say there's a system which can take 4 states, A, B, C, and D. And there are likelihoods of states which are already known. We already know that system A would be, it will take state A 80% of the time, state B 15% of the time, and so on. The D is the least likeliest state, and you'd be very surprised to find whenever you observe that system, let's say you not very frequently you observe it, but if you find it in D, you'll be surprised. Oh, it's just 1%. Its occurrence is 1%, and we found it. So the amount of surprise is inversely proportional to probability. That we can conclude. So what a guy named Claude Shannon in 1948 did, that he tried to quantify this surprise. He said that if amount of surprise is inversely proportional to probability of occurrence for any system, then let's quantify it by saying log of 1 by p is my surprise. And given that you have the distribution of states available and their likelihoods, you can, in the long run, if you keep observing the system, you'll arrive at a quantity called summation p log 1 by p. Log 1 by p is the surprise associated, and p is the likelihood of occurrence that we already know. So this quantity is called Shannon's entropy. It has now what it quantifies is that what is the average amount of surprise in a time series or a distribution whenever a new state is taken. So whenever a new value is generated, how much surprise, how much uncertainty is actually generated. So now entropy of any distribution is like a is like a Venn diagram from set theory. Whenever two variables are interacting with each other, if two variables have some predictive information for another, if for example, if I can write y as a function of x, I don't know what that function looks like, but if at all that function exists, then the entropies of x and y will overlap with each other. This overlapping region is called mutual information, right? And if mutual information comes out to be zero, then it has been argued that mutual information is actually a measure of true independence. It's not correlation or partial correlation, because here we don't make any assumption about the type of link, linear or non-linear. So if mutual information comes out to be zero, nothing exists between two time series. So now if we keep on increasing the variables in this Venn diagram, imagine that I have 4 variables here, and still some overlap remains between unique overlap remains between y and x. Let's say we included z, we included p, q, d, which kept on covering this overlap, and still some unique overlap remains. This unique overlap is called conditional mutual information. Conditional as in you condition on all the other variables which are present, and what remains now is pure connection between x and y, pure predictive information between x and y. This is called conditional mutual information. It has been argued that it's a measure of direct causal association in a predictive sense, like Granger causality. So if z variable here, I put the z variable as a lagged version of x or y, not any third variable, then this is also called transfer entropy. Now, since it was also the intuition behind everything that I told you was again to do with prediction, that yes, we can write a function of some form if there is an overlap. So Granger causality and transfer entropy are actually equivalent for each other for Gaussian variables. It has been shown. But the problem with information theoretic methods is that there is a curse of dimensionality involved, and escaping it is a bit tricky, still tricky, because with large number of variables, we start to lose statistical power. So next comes another method called convergent cross-mapping. Now, all of you must have seen at some point of time, out of curiosity, that there is something called butterfly effect from chaos theory, the nonlinear dynamics. So in deterministic systems, and this is called an attractor or state space diagram. The state space can be constructed out of a variable if a variable belongs to a nonlinear dynamical system. So the method of convergent cross-mapping relies on the fact that if two variables are causing each other, one variable's state space can be used to predict another variable's state space. So there is something called simplex transformation, simplex method, or Takin's theorem. It tries to generate a state space diagram out of the time series that you have. So assuming that the variable that you are studying comes from a nonlinear dynamical system, and you try to find out if you can generate another variable's state space using one variable, then you can say that this variable x causes y, if x can be used to generate the state space of y. That's the intuition behind convergent cross-mapping. So we have discussed three methods till now: Granger causality, nonlinear state space methods, which I just explained, and some information theory based methods. Another methods which exist are something called causal network learning algorithms. What they do is they start from a fully connected graph. They assume that with some prior knowledge maybe or not, there's a fully connected network, and you iterate through this network. You then start conditioning. You take up the strongest link and condition everything else on it. And you see if everything else links are getting removed. So this iterative process, when it converges, you decide that there is something that you have discovered the skeleton of the causal structure. And then again, you perform some conditional independence tests to find out the exact orientations of that causal structure. And this whole system performs causal discovery. And then there is something called structural causal models. Now, these are slightly different because they assume that what we need to have here is that we need to have an equation already between two variables. These are called structural equations. What is the use of structural causal model is that we can test interventions like that. So if you already have equations available, structural equations for each link, then these are called structural causal models, and you can test interventions in them. If you what if I change this, how would the system behave, and things like that. So here is a causal network learning algorithm called PCMCI. It was generated by a guy named Jakob Runge, and what it does is, like I said, the curse of dimensionality is a big problem for almost all methods. And why is it a problem? Because some conditioning is involved, like I said. So if you keep conditioning, then you'll have to generate joint probability distribution. So to perform a conditioning of 3, I have to find out x comma y comma z. That is like finding out a joint probability distribution between x, y, and z. So as dimensions keep on increasing, computing joint PDFs becomes very, very, very expensive. So what it tries to do is, what this algorithm does is, it tries to split everything into 2 parts. So first, we have recognized that there is a problem of high dimensionality. Everything that is available is not necessarily useful. So what it tries to do is, it uses something called PC algorithm to reduce the conditioning set. So what we are going to condition on will be a reduced thing. So it iteratively does that, starts from a fully connected graph, like I explained, and then for each variables, like for this black node here, it will try to find out what are the something called parents. And in the end, what will happen is, due to the assumptions that I told you, Markovian and faithfulness, if you condition on parents, everything else is unnecessary. They need not be included. So our conditioning set reduces drastically from full data set to merely two, three variables. So for each variable, a parent will be generated. So this step tries to reduce the conditioning set. And in the next step, they called MCI stage, it tries to find out the causal inferences by conditioning on all the parents that we have generated in the previous set. So for example, it will try to find this link by conditioning on everything else. It will try to find this link by conditioning on everything else, and so on. So in the end, we'll arrive at some causal structure. And to perform conditional independence test, there are metrics that can be used. So if you want it to be linear, you can use partial correlation. If you assume that the data set has linear associations. And if you want, you can use conditional mutual information as well from information theory, like I just recently just explained a few slides ago. Here are some more causal discovery methods available. You can look them up in the latest review paper by Jakob Runge, the group, and it's called Causal Inference for Time Series. So they list all the methods that are available with open source softwares to perform them. And so there's something called PCMCI. It has been evolved to PCMCI plus LPCMCI. If there are hidden confounders, you don't know what confounders are. It tries to address that challenge. Then there are something called score-based methods, which I did not discuss. What score-based methods do is that they generate multiple sets of graphs and try to score them based on how well do they fit some observed data set or some known information. There are something called asymmetry-based approaches, and there is something called invariance causal models again. But I mean, these are you all can find a good description of them in the latest review paper. Moving on to case study. Now we have a good idea of what causal tools are available. I'll show you some of the objectives, 2 of my objectives from the work that I have carried out. So one of the works explored the implications of India's ambitious river interlinking scheme considering land atmosphere feedback. So what's the problem at hand here is that India has this ambitious plan to interlink all the major river basins. The goal, most primary goal, is to increase irrigation across country to generate maximum agricultural output. Now, there are also hidden benefits like electricity generation, water supply, but the most primary goal is to increase irrigation. So what we hypothesized is, what if river basins are already linked by land atmosphere feedback? What if there are causal connections between river basins? What would happen to them if we irrigate, if we keep maximum water on land? So that's the purpose of these projects. So the water that used to go earlier into Arabian Sea or Bay of Bengal, they want to keep it on land and keep evaporating it. So what are the consequences of the pre-existing causal structure? What we found is, we consider these 6 river basins. On each river basins, we consider these hydrometeorological variables: latent heat, sensible heat, soil moisture. These 3 are on land. And then there are some atmospheric variables: relative humidity, shortwave radiation, wind speed, temperature, precipitation. And these are the basins considered. So what we tried to find out is, for each river basins, we had these 8 variables, and so around 48 time series. We tried to find out if there's a causal structure that exists between them. What we found is that there are within basin connections. So LH_G means latent heat flux from Ganga basin, and SH_G means sensible heat flux from Ganga basin. So there are within basin connections from land to atmospheric variables. So this is relative humidity, shortwave radiation. So there are within basin upward connection, and then there are cross basin atmosphere to atmosphere connections. So for example, latent heat in Ganga basin contributes to precipitation in Ganga basin, but simultaneously it is also related to solar radiation of Mahanadi basin. So as winds carry moisture to different river basins, they can change the cloud formation there, and hence solar radiation, which can ultimately lead to changes in latent heat flux on land of Mahanadi basin. So these kinds of pathways are already existing before you interlink rivers. So next, we hypothesize that since prior links already exist between river basins, if we physically transfer water from one basin to another, shouldn't these links actually lead to changes in other basins as well, if these links exist? So this is what we hypothesized, and we tested it using a regional climate model, VERF CLM. And what we found is, in the September month, there is a significant change in rainfall in most of the parts of our country. So why this appears in only September month? Because literature shows it is already well known that in September month, the land atmosphere feedback peaks in the monsoon. So Indian summer monsoon, 25% of the rainfall that happens during Indian summer monsoon comes from land only. So it is obvious, means it's intuitive that we would find most of the significant changes during the month of September. But what was surprising is that there is going to be some drying in some parts of the country, and some of these regions have nothing to do with where irrigation was applied. So this figure here shows where irrigation is being applied, and some parts of the country which are not involved in these projects might also get dry, because this is primarily because land atmosphere feedback is getting redistributed. So what we found is that there is up to 11% reduction of September rain in central India, and simultaneously there is an increase in the rainfall as well. So in Ganga basin, for example, the rainfall increases up to 12% in this region. So this increase has consequences towards floods, and this reduction has consequences for water availability. Since post-September, the river starts to become dry. If these regions get less rainfall in the month of September, then post-monsoon water availability can be a challenge. So this was a surprising finding, and a kind of non-intuitive result, unintended consequence of river interlinking. What could be the potential remedy? It's simply that if we include these budgets while planning for water transfer, that could simply be a solution to this. So the conclusion was that there's a need for model-guided impact assessment studies and including land atmosphere feedbacks while planning large-scale hydrologic projects like river interlinking. So this schematic shows how these moisture transfer can affect. So if we conduct an interbasin water transfer and we perform additional irrigation, so it can lead to increased evapotranspiration. And then since moisture transport is already happening, it can lead to rainfall anywhere, since rainfall has no specific pattern. The next case study that I'm going to show you has to do with global drought teleconnections. So there is this study which showed that these are the hotspot regions of global drought teleconnections. So they used something called event synchronization. It's a very simply a counting technique which tries to find out how many significant number of times this number was droughts here were synchronized with any other regions across the globe. Based on this, the highlighted regions mean that they have the highest amount of synchronization. So this region has highest amount of synchronization. Whenever drought occurs here, somewhere else on planet Earth, drought is also going to occur within 6 months. That's what this means, the synchronization. So these are called drought hubs or teleconnection hotspots. So what we thought was, what if the most dominant hubs of drought are in the ocean, not on land, since oceans were excluded from the analysis. And what we found was, indeed, when we only consider land variables using event synchronization, we do get these links, these hotspot regions. But if we include the oceans, the biggest hotspot are actually in the ocean, not on land. And most of the connections are from Indo-Pacific worm pool or the maritime continent or the Central Pacific Ocean. But the important thing that I want to discuss with you is that we also applied causal discovery algorithm to these regions, these important regions on land as well as the ocean. And the metric used here was precipitation. So standardized precipitation index from all these regions, and we tried to find causal connections between them, but in case-by-case basis. So first we only considered land variables, and then we kept adding ocean variables incrementally to our network. What we found is that as soon as we add Atlantic Ocean, this land link vanishes. So earlier there was a link from South American monsoon, SAM, South American rainfall, to ME is Middle East. So which vanished once Atlantic Ocean AT was added to the network, which shows that oceans can act as confounders to these links. So as I explained to you, if there's a common driver bit of these two links, then this link can appear and it would be spurious. So this is these kinds of inferences can be made using causal discovery algorithms. What are the challenges that lie in causal discovery approaches? There are some challenges which have to do with time-varying causal associations. A lot of work has been done already, but a lot of things need to be explored. For example, there is an interaction of El Nino with global monsoons or global teleconnections. It's not fixed in time. It varies from season to season, and that seasonality is also sometimes not known. It sometimes misses. So these kinds of associations are yet to be explored thoroughly. Then there is interactions at different time scales. Can causal relationships exist from intra-seasonal variability to interannual time scales, or maybe coarser time scales, or vice versa? How is the causal structure at varying time scales? Next is varying distributions. So causality of extremes. How does causality of extremes differ from causality of means? And how does the distribution of noise fit into all this? The next is what if there are synergistic behaviors? Synergy means whether if there are two variables acting simultaneously, then only we achieve a signal. If one of the variables is absent, the signal is absent. That's synergy. So what do we have for synergistic behaviors? And then there is an effect of unobserved variables. Like I told you, that it leads to violation of an assumption called causal sufficiency. So how do you handle that? And then the most important one is the lack of benchmark and validation platforms for results. If you are doing a causal analysis for an unknown system, you don't have an observed causal structure a priori. So all you have is your causal algorithm to trust. So since there are no benchmarks are available, questions can be raised on whether or not the causal structures are true. But recently, some benchmarking platform called causeme.net has been proposed, and where most of the causal discovery algorithms are being benchmarked against pre-generated problems or already known causal structures. I hope this has been helpful, and these are the references. Thank you. If you have any questions, I'd be happy to answer.
Thank you, Tejasvi. If audience have any question, they can raise their hand. I can make them unmute themselves. And there is a question like, will this presentation be made available for later viewing? Yeah, we are recording, and we'll make sure the recording will be available online. Okay, there is. Okay, there's a question from Dr. Pankaj Dey. I had unmuted himself, I believe. Okay, yeah. And Dr. Pankaj Dey, can you able to speak? Okay, Professor Brahma, you
Oh
have any
yeah, yeah.
question?
Okay,
Yeah,
can you guys hear me?
yeah.
Yeah.
Yes.
Yeah. Great talk, Tejasvi. Really enjoyed. So I wanted to ask that what was the precursor, or how did you choose those eight variables? In the river interlinking project. For example, we could also add groundwater, which is heavily exploited in India as one
Yeah.
of the variables, right?
Yes.
Yeah.
So the thing is that here timescales are important. Like I told you that in limitations, if timescales are way far away, let's say some quantity varies at annual timescales, and my interest of variables of vary at daily to weekly timescales, then they including both of them becomes problematic. So including groundwater here would mean that since groundwater in the variability of groundwater is at very low frequency, natural variability. So if you even if you include groundwater here, it won't show much change. Only change would be just based on variability of human interventions in groundwater. Am I making sense?
Yeah. So that was the thing, because a lot
Yes.
of irrigation in India is actually driven by groundwater. It actually acts. Then it goes to the land atmosphere feedback, and recycle precipitation. Soil has done a lot
Yes.
on that front, right?
So that
So all
irrigation
that would
is
also play a role, right?
yes. So all that irrigation is already present in the control run. So the
Okay.
WRF's control run already includes this irrigation by which is by default being done using groundwater. So the intervention run, which applies irrigation over and above the previously occurring irrigation, tries to apply the irrigation from surface of taking water balance of surface of rivers, river
Okay.
discharge. So when you try to find out these kinds of connections from WRF simulations where groundwater was already applied as irrigation, these links remain more or less the same. Nothing changes.
Okay. Okay. Thank you.
And Mr. Vivek Kumar, okay, he already had a question in the chat. I also,
Thank you. Tejasvi, allow me to thank you for this very
I cannot hear you, Vivek.
yeah, I cannot, so maybe he got stuck. But he had a question here in the chat. If you have a doubt, yeah, if you want to answer.
Okay. Okay, so for getting an equation, So there is something called, to get an equation, what you have to do is cause effect estimation. So, but there also some assumptions have to be made first. For example, I'm assuming that the equation would look like this, and then I'll estimate the parameters. So these methods try to find out strength of associations, and these method here, VAR, so linear non-Gaussian acyclic metrics, and something like that it's called. These start from an equation and estimate an equation in the end for causality. Through PCMCI, what you'll get is you'll get an estimate of the strength, not an equation. But there are methods which try to do that. For example, one of these methods is Varlingam, and then there are structural causal models which try to do that. I hope that answers the question.
There is a question from Ashwant. Okay, there is a second question from Vivek.
Yes.
Yeah, I hope you can see, or do you want me to read the question for you?
Wait a second. Okay, yeah, causal sufficiency is the most trickiest part, because so Vivek has asked that do you encounter some problems while selecting variables due to various conditions, for example, causal sufficiency. So causal sufficiency is something that is left in general to the judgment of a researcher. So if I show you something like from the latest review paper by which I just mentioned, here is the schematic which shows how to go about a causal inference, how to go about any causal inference problem. So even if the causal sufficiency is not being satisfied, there are methods to do about it, but you need to address them, that what would be the limitations because of that. In my case, the causal sufficiency was justified because as per literature, all of the variables that are necessary for land atmosphere feedback have been included. So it was plain and simple in this case. But in general, yes, that's a problem, and this is where you can spend most time before generating a running a causal algorithm, to make sure that you have the variables all that are necessary. Any other question?
There is a question from Ishwant.
Okay.
Yeah.
So you have 6 atmospheric variables and max lag 12. Yes, so that means that 72 dimensions. So that becomes too big a problem. And perhaps you can try PCMCI. I don't know if. Okay. He says that through nonlinear CMI it takes too much time. So yeah, time is a problem in conditional mutual information. One way to do is to try to parallelize your code. So there is a module in that. If you can run it in parallel, it will be very efficient. I think 1/4 or 1/3 of the time that can be done. That can be one thing that I can suggest right now.
Okay, I have a question. I think it's in the same line with the next question regarding the can we apply causal model for limited number of observations? Usually, like I work in flood especially. I only consider one value per season, like kind of seasonal maxima or annual maxima. Yeah, it is limited, and also it is not continuous, because some people, they don't accept it as a continuous variable, unlike a daily series. So would you still suggest causal techniques for that to identify any
I think it comes
drivers?
down to time scales. So if you have one value for a season and sufficiently long time series, then it just means that if you use it, you're going to get relationships at interannual timescales. You cannot expect intra-seasonal links from this relationship. That's all. If so, that would be a limitation, because that would be a data limitation. Means we won't be able to do anything about it. So, but interannual results, definitely you can.
Oh, is there any limit? Like, cause usually in the flood we have a kind of thumb rule. We use 30 years data. I mean, so it's basically like 30 values in a time series.
Okay. I'll explain that. So it varies from method to method. So a ballpark estimate that has been given for transfer entropy is around 500 values. 400 to 500 values, if they are present, it is good enough. So that's why data requirements are high. But for convergent cross mapping, it's very low. So as low as it has been applied to ecological time series with values as low as 30 to 50 values. That's all. And for PCMCI, I think it would be somewhere in between 100 values. That would be my guess.
Okay, I have unmuted Ravi.
I think Pankaj said that
Ravi.
he is connected now.
Okay, yeah. I don't know. I can able to unmute himself, but again, it's got muted. I don't know why.
Oh.
So may I ask a question meanwhile?
Sure, Dr. Ravi.
Thank you, Tejasvi, for the wonderful talk. Really, lots of learning from you. And I have a question related to technical aspects associated with information theory. So when we have these two variables, we have this concept of binning, right?
Yes.
So for two variables, like how did you manage to find the optimal bin width for the both variables?
There is a thumb rule for that. Square root of number of data points available and something to do with the dimensions. I don't recall. I can send it to you. But in general, it has been shown that if you fit non-parametric distributions instead of binning, that works much better. Do you understand? Kernel density estimate.
But the the interpretations from the information theory is mostly associated with the binning. That's what my understanding is. Yeah.
So there's a thumb rule that it should be. I am not able to recall. Maybe I can share it with you. But there's a thumb rule square root of length of time series. It scales with square root of.
So here the logic. I mean, what I'm trying to understand is that we have these two variables. The distributions may vary. For instance, say, okay, I'm looking at precipitation and I'm looking at temperature. For instance, one follows a skew distribution and the another follows a normal distribution.
Yes.
Right. Now, how do we find an optimal solution to come up with a optimal bin width? That plays a crucial role in determining the causality or causality from one variable, how it is translating to another variable. The number of bins, the state of information, how it is getting translated. It's really important.
Yes.
So
I agree.
So
means there is no.
So I'll also follow. Yeah.
I mean, we can discuss it, but there is no standard rule for binning. I've read a lot, but there's only that thumb rule which scales with square root of time series that exists. But I think it's all up to the judgment of. So it depends on how big a time series do you have. If it is sufficiently long enough that information theory. See, the purpose is, why does distribution or metric scale with binning? It is because you don't have true distribution, right? If you can generate true distribution, then that is what you should use actually to get the metric, like mutual information or entropy. The goal of information theory is generate a true distribution out of sample, and then using that true distribution, you'll get some entropy, and its overlaps will be mutual information. Since binning, so my answer to this question would be, plot the time series and histogram and see if distribution looks like if it's sufficiently long enough time series, then the distribution should not change with bin width. If it is changing a lot, then the results will definitely not be reliable. Then we can use a thumb rule, definitely, but to do that, but it will change a lot. That's what I have experienced. It changes a lot.
I completely agree with you. That works out for a univariate scenario. So for the univariate situation, the distribution won't change. Even it is not sensitive to the number of bin widths. But here the problem is, when two variables come into picture, that creates a. So are there any sensitive experiments in your research work so that we can follow?
Yes, there is not in my work, but there is a sensitivity work by a group from Professor Praveen Kumar in UIUC, Illinois.
Please, I'll get in touch with you. We can see some great collaboration in future.
Great. Looking forward.
Thank you so much, Tejasvi.
Thank you. And then there's question by Vivek.
Should we write here? हाथ नहीं दिख रहा क्या इन लोगों को?
Once they call, we can
Maybe we can take Pankaj's question. Suppose you have one discrete variable and many continuous variables. Yeah, so discrete and continuous is two different things. Means it won't be possible to do discrete in information theory, but you can do that. PCMCI does that. So there is a since for discrete variables you can get you can generate a distribution, but it won't fit in conventional sense. But PCMCI has a module called CMI symbolic, conditional mutual information for symbolic time series. It tries to fit a binomial distribution to bivariate a binomial distribution if the states are two, and some kinds of categorical distribution, discrete distribution to do that. But there is something called CMI symbolical which does that. It would be good if I can talk to them if they can speak. Avinash, can you unmute them?
Yeah, I
Hello.
can.
Hello. Yes.
Hello, am I audible?
Yeah. Is this Pankaj? Hi, Pankaj.
Yes. Hi, Tejasvi. Very nice presentation.
Thank you.
So yeah, the first question you answered, it was logical, and the second question was like during my research on the causality, what I found is that this long-term memory, it's one of the crucial player that decides whether your algorithm works fine or not. So even for a simple bivariate case, like suppose X and Y, if I take, and suppose I make artificial time series by imposing different level of long-term memory in that.
Yes.
And when I know the causal structure and I test this causal structure in presence of conventional methods, for example, Granger causality or transfer entropy. So what I found is they are not able to identify the true causality. That is X is causing Y. So this is in bivariate case, I found this, and I believe when the system become more complex, that is where multiple variables are interacting, this phenomena will enlarge or have some very difficulty to account it in any method. So I want to know like how we should proceed, or how do we think to take care of this, because long-term memory is one where we can actually do prediction for longer timescales, and it is a very intrinsic nature of any art system science variables.
I agree. I completely agree with you that if there are long-term variabilities involved and they have not been removed, then it changes. So there's something still limitations exist in these methods. I agree, Pankaj.
Yeah.
And
Thank you.
there is one more question from Akshay. I mean, he's raising hand. I unmuted him.
Yeah, hi.
Yeah.
Am I audible?
Yeah, you are.
Yes.
Yeah, so the presentation was very informative. So I have a question like from the point of view of a decision maker. So when it comes to interbasin water transfer, so these are projects which are actually planned in the long run. Some of them have already been started. So what I understand about climate and the dynamics and about the variables is that the dynamics of these variables keep on changing because we are getting to know more information about the temperatures keeping on rising, and because of that the interplay or the connections between these variables keep on changing. So post interbasin water transfer also the variables keep on changing, and because of this I think the causality can change. So like what is your recommendation for setting up or continuing the interbasin water transfer? So I'm just asking from an expert opinion for a decision maker to do. Yeah.
I agree. That's an excellent question. So that is true that causal links can change over time. So what would be the ideal thing to do is causality can give you an indication that these links are already related to each other. But model simulations can definitely give a physics-based guidance on that. So when we estimate interbasin transfers, we use historical discharges. But what if you ran some future simulations and with interbasin transfers, how discharges are going to change? That should be one simple way to start with it. That I would suggest. Causal connections will keep on changing with time. That I agree. For that, more research would be needed. Like I told, that time varying causal associations is still a problem in causal inference.
Yeah.
I hope I could answer.
Yeah. It's a good suggestion from your end. And one more question I had in my mind is that, like, if hypothetically we have to create a weather model, a very local weather model, for example, a hyperlocal weather forecast. So then too, we'll have to consider the local level variables, and then there are actually interactions of variables of different spatial scales with these variables too. So, for example, if I'll keep this very, very basic. So if I have to predict, hypothetically, if I have to predict the rainfall, and if I am using the cloud cover as an input variable, so out of the causal mechanisms you just explained, like, so there is a particular lag. For example, a cloud cover at this present time step might be contributing to rainfall after 1 hour. So if I'm taking this assumption, so how do you figure out these lags, and what would be a good algorithm to find this out? Yeah.
Lags, see, it depends on what method are you using. If you were using Granger causality, then lag have to be known at least intuitively a priori, that what is the maximum amount of lag within which I'm going to find a significant contribution. So let's say by judgment, I can say that if cloud leads to rain, it may take up to 3 hours or 4 hours. So I'll use 4 lags. But so that's one way to do it. Next would be let the algorithm figure it out. So for example, PC algorithm does that. The method that I explained, PCMCI, its first step where the parents are generated, it tries to do that for every lag. So it will automatically find out the best lag at which the most significant connection exists and preserve that for the conditioning set. Does it make sense?
It makes sense. So the intuitive approach is what generally we do, but again, if the algorithm is able to give the lag, because the interactions between different variables happen at different time scales, and if the algorithm is able to give the lag, I think that will be a reliable input to the forecast.
See, for the problem here is that for you to ask an algorithm to give me the lag, that simply means you are asking algorithm to check at how many lags. So when should algorithms stop checking? That would be the only thing.
So
most of the algorithms do that. They give you the lag, but you need to provide it. When do you stop? If you don't give that number, then there would be infinite lags to test. That would just create some computational problems. I hope it makes sense.
Yeah, it makes sense. Yeah. Okay. Yeah, that's all I had to ask.
Thank you.
You're welcome.
Yes, I can. Can Vivek be unmuted? Abhinesh?
Just a moment. Okay. Yeah. He was unmuted.
Hi, Vivek.
Okay. Is there any other question from?
Okay, then there's a question from Ojas. We saw drought hubs shifted when we include ocean data. What was the major region for drought hubs in the ocean? Is it reduced precipitation or cloud cover? So cloud cover data I have not included. All I've used is precipitation. So I converted precipitation into something called standardized precipitation index, from which we can infer when the deficit was there. So that deficit is the drought. So from precipitation. So Vivek's question is, if I include the groundwater, what effect would you think would you have it in the final graph? Suppose the link from groundwater should be very weak, and algorithm eliminates it. So there are two things here. One, like Pankaj mentioned, that if a long-term variability, the variable with long-term variability is introduced, the algorithm does not know what to do with it, since there is no significant causal connection within the timescales you are trying to study. So for a land atmosphere interactions, you'll try to study maybe 10 lakhs, at most 20 lakhs, since atmospheric residence time of moisture is 10 days in general. But for groundwater, it's entirely different. So it's having such a variable which varies very, very slowly. I don't even know how algorithm would handle it. Means it would be, in my opinion, it would give some spurious links. I won't trust the link that comes out of putting groundwater in there, because it's a very slow varying variable, and the variability, time scale of variability that I'm trying to study in right now doesn't fit in that paradigm. I hope it answers. I'm not able to understand why we are not able to unmute him.
I can unmute, but he got again muted because there was some noise from his. Is it that Vivek, or I don't know?
I hope I could answer your question.
Okay,
Yeah,
okay, you answered. And I have one question, Tejasvi. Like you showed the after interlinking effect. I noticed a strong decrease in the precipitation in Pakistan and all.
Yes.
So I mean, it goes up to -40%. It was huge.
Yeah. Yes.
Why is it so?
Yeah, that is not statistically significant at all. So this region is partially, but this is not. So if statistical significance is not established, it could just be an artifact, not means it could just be out of randomness for this region. This is an arid region. So for a 40% change, only even 1 millimeter of rainfall, 2 millimeter of rainfall could also bring that change. Means a few millimeters of rainfall could bring that change. Does it make sense?
Yeah.
So it's so arid that even small changes reflect as higher percentages. That's why there is not much statistical significance in this region.
Okay, that audio was not this. Okay, fine. And okay, he again raised his hand. I unmuted him. Vivek, can you able to speak now?
Yeah, yeah, but my questions are now done. So thank you, Tejasvi. It was very informative.
Thank you.
Yeah. There is a hand raise from Akshay. I unmuted him. Hello, Akshay.
Hi, so I had one more doubt. Like in the previous slide you showed now, showing the spatial variation of rainfall, I mean post interbasin water transfers. So
yes.
Is that plotted? I mean, is it the simulation of a WRF model you plotted in that? Is it the spatial distribution of rainfall which has been simulated using WRF model?
Yes.
Okay, so it's basically a simulation taking into consideration all the global variations.
Yes, global variations are given as boundary conditions. We make
Okay,
up for India. So the boundary conditions are initial and boundary conditions are from global data sets observed reanalysis era interim.
Yeah, and for then testing the causality of different variables, like the variables of what grids were considered. For example, yeah.
Or in model simulations or in, so there are two things.
In causality test.
So for causality, I selected variables over these regions, averaged over each river basin, the marked with colors. So I averaged land and meteorological variables over Ganga, Godavari, Mahanadi, and so on.
But doesn't the variables of other grids also affect the precipitation in these grids? For example,
yes, that
yeah.
you are correct. So grids here will also be related. Our goal was to, in a systematic way, identify whether river interlinking will cause a problem. So we considered only those river basins which were involved in river interlinking, since the goal was to show whether or not they are connected to each other. In principle, yes, this region will also be connected to Ganga. So it will be much more complex than this figure that you see. It will be much more complex than what is shown here.
Yes, because I was asking this because, see, it's supposedly to rain in Maharashtra and regions towards the Konkan coast in 2 days. So in 26 and 27. So that is because of interactions that happened in the Mediterranean region.
Yes.
And again, there are interactions. What happens basically is the easterly winds will meet the disturbances from the Mediterranean, and that's causing the rainfall distribution in this winter period. So it's actually a bit complex than that, but I understand that you are doing it specifically for the interbasin case study. Okay, that was very, very informative. Thanks for sharing the information.
Thank you. I think there are some.
Okay, I don't see any hand raise.
Oh, there was a question by Vivek. Can we apply it for limited number of observations? I think you covered it. So it depends on the technique, like I answered, that we are using. So are there no questions, Abhinesh, right?
Hello.
Hello. I think one hand was raised. Okay, no. Yeah. Vivek, I think Vivek has raised a hand. Abhinesh, can you unmute him?
Hi, Tejasvi. I'm interested in trying with a few of my data. So are the codes and packages available kind of like freeware on GitHub or somewhere?
Yes. The one I used, PCMCI, it's freely available as a package called Tigramite, Tigramite. But you can look up the recent paper from Jakob Runge's group. It's called Causal Inference for Time Series. It documents all the open source softwares for most of the causal methods. So whatever you want to decide to use, and there's a framework how to decide your method as well, for how to decide your method as well. Maybe you can look up that. But all of the codes are publicly available freely. Yes.
Okay. Is there any other question? I can't see any. Can you? Tejasvi?
No, I cannot.
Okay. Cool. So thank you, Tejasvi, for the great presentation, and once again, congratulations for your postdoc.
Thank you.
Yeah,
thank you.
it was
Thank
really
you,
wonderful.
India, for giving me this chance.
Yeah, and I request everyone to click on the link which is posted in the chat box. You know, it's a Google form. You can fill the form for future updates. It's an old form. If you have not got the email regularly from us, then you need to fill it. Okay. Then see you in some future webinars. Have a great weekend, everyone. Bye.
Thank you. Thank you. Bye.